This is Tuesday, May 2nd. We're continuing with the Unit 3 notes, or 9.3 notes, okay? So we talked about Maggie and Elizabeth's bag of M&Ms, right? Okay, copyright, I don't know who has the copyright to M&Ms, okay? So let's keep going through this. In general, since the two bags are independent, right, if like whatever M&M I pull out of Maggie's bag does not affect the probabilities of pulling all the M&Ms out of Elizabeth's bag, that means my two events are independent. So what I'm doing in general is I'm treating Maggie and Elizabeth's bag separately, and to get the answer to one of these problems, I multiply the two probabilities, okay? So let's look at that specifically. If a candy is chosen from each bag, what's the probability that neither will be brown, okay? So first let's start, if I pull an M&M from Maggie's bag, what's the probability that it's not going to be brown? It'd be 0.8, right? 1 minus 0.2 gives me 0.8. So 0.8, okay? If I pull an M&M out of Elizabeth's bag, what's the probability that it's not going to be brown? 0.9, and then I do what? My final answer, if we want neither of them to be brown, these are independent events, I do what here? Times, yep. So it's 0.8 times 0.9. 0.8 times 0.9. 0.8 times 0.9. 0.8 times 0.9. Okay, I got 0.72. 72% chance that neither will be brown. Does that make sense? Hey, haircut? Good, man. Okay. So if a candy is chosen from each bag, what's the probability the first will be green, the second will be blue, okay? So let's make Maggie's bag the first bag. What's the probability that the M&M I pull out of Maggie's bag is green? 0.3, right? What's the probability that the blue, I pull a blue out of Elizabeth's? 0.2. What do I do with those two to combine them? What do I do then for my final answer with those two numbers? Multiply. Right? We multiply because there's an and here. And they're independent. Okay? In general, if it's the first one's green and the second one's blue, we multiply them. I got 0.06. So 6% chance. Does that make sense? If a candy is chosen from each bag, what's the probability? Oh, here's a good one. That one will be blue and one will be green. So what are the two ways of getting one blue and one green? There's actually two ways to do this. We could pull a blue out of Maggie's bag and a green out of Elizabeth's bag, or we could pull a green out of Maggie's bag and a blue out of Elizabeth's bag, right? So we want either or those. Okay, so yeah. If one of those two situations happens, we'll get a success. So how do I want to say this? Let's do the probability. So let's just do the probability that we get. Okay, so two ways of doing this, two ways of this happening. Two ways of this happening. The first way is a blue from Maggie and a green from Elizabeth. Okay, what's the probability for that? Did we just say that? Is that just so blue from Maggie's? Okay, 0.1 times the green from Elizabeth's is 0.2. You guys following? Okay, 0.1 times 0.2. 0.02. So that's 0.02% chance, okay? Second way is vice versa. Green from Maggie and a blue from Liz. What's that probability? That we just did that right here, right? 0.06. Right, green from Maggie, blue from Liz. 0.3 times 0.2 gives us 0.06. Okay. So we want the total probability of either the first one happening or the second situation happening, right? Or, what do I do with or? I add. So it's 0.02 plus 0.06. 0.08. 8% chance. Okay. All right, that's because there's two different ways of that happening. That make sense? If a candy is chosen from each bag, what's the probability that neither will be red? Okay, so we need to do the probability of pulling a non-red from the first bag and a non-red from the second bag, right? So what's the probability of getting a non-red from Maggie's bag? Anything but a red, 0.8. What's the probability of getting a non-red from Liz's bag? 0.7, and I'm going to multiply the two together because they're asking me what's the probability of both of those occurring. The first event occurring, the 80% event occurring, and the 70% event occurring. So I got 0.56. Is that what you guys got? Good stuff. Good stuff. Nice squad. Okay. We're going to move on. We're going to do a little bit of combinatorics. You guys okay if I move on to this card deck stuff? Here we go. Okay. Consider being dealt a 5-card hand from a standard deck of cards. How many 5-card hands are possible?
Choose 5.
52 choose 5 or 52 factorial? Choose. Why is it choose and not, why is it a combination and not a permutation? It's because order doesn't matter, right? If I'm dealt 2 jacks and like 3 aces, that's the same hand as if I'm dealt like the same 3 aces and then the second 2 jacks, right? So this one is 52 C5. 52 C5. What's that? $52C5. I got 2,598,960. Five card hands. Does that make sense? Makes sense. It's good. What's the probability of being dealt a hand with all diamonds? This is really interesting.
13 diamonds, 10.
All right, let's think about this. Wait, what? How many diamonds are there? Yeah, there's 13. There's 13 diamonds. So the way you do this is we're going to do a fraction. The denominator is going to be the total number of hands possible. Okay? So 52, choose 5, right? Okay, that's going to be the denominator. Okay. How many all diamond hands are there possible? How many all diamond hands are there?
1.
No. It's five card hand.
2. 3.
There you go. Yeah. Right. So if I only had 13 cards, and they're all diamonds, right? The total number of 5-card like combinations is 13 choose 5. So there are 13 choose 5 all diamond hands possible. Okay, and that's out of the 52 choose 5 like total hands possible, right? So if there's an equal probability of all like getting like any particular hand, wait, let me explain it this way. There are 50 choose 5 total hands possible. 13 choose 5 of those are all diamond hands. So I divide number of all diamond hands divided by total number possible, okay? So this was number of diamond, number of all diamond over number possible. Does that make sense? Okay, so let's do that. 13 choose 5. 52 choose 5. I got, it's pretty low probability. I got 0.0005. Okay, were you good? Not good? I more care about that you're following my math. Rather than, I don't care if you're making kind of mistakes. 13 choose 5 over, okay, that's, you got the exact same thing I did.
Oh, I did?
Yeah, you got it in scientific notation. Is that okay? Are we doing okay? We're not doing okay? Okay. I don't want you guys to be confused. Okay. What's the probability of being dealt a hand with all face cards, okay? So let's do this again, okay? There are 52 choose 5 hands, total hands possible. Out of all those possible hands, how many are all face cards? How many face cards are there in a deck?
12.
Are there 12? What is it? Jack,
Aces count.
king, queen, jack, queen, king. Do you count an ace as a face card?
No.
I have a question. On the test, are we gonna have like stuff like this?
Yeah.
But are you gonna like give us stuff we like know? Like what if we don't know how many?
Like how many face cards there are in a deck?
There are, yeah.
Then you just gotta just play more cards. No, I don't know. Sure, I'm okay giving that to you. I want to test you over your ability to do math, not like over your knowledge of the standard 52 card deck. So, yeah, I personally would feel conscientious.
You could just do like if you did do this, would you put like there's 12 face cards?
Yeah, I would feel comfortable saying that. This is 12 choose 5 then. Okay, does that make sense? So the total number of face card hands possible divided by the total number of any hand. Okay. That's what I want you guys to follow here. Okay, number of success over number of trials. Probability of being dealt an all red hand. How many red cards are there?
26.
26. So it's 26 choose 5 out of 52 choose 5. These are huge numbers. These numbers are huge. There's a number called Graham's number that if you were to think of every single digit at once, the information and the density of your brain would be so big that it would collapse into a black hole. That's what my physics professor told me. Isn't that crazy?
How's that?
How do you collapse into black? I thought black holes were in space.
No, a black hole is any object whose density is like above a certain amount. What happens is like if the gravity is like so strong centered at a given point. Yeah, that's what it is. It's any object whose mass is like compacted into a point whose radius is smaller than what's called a Schwarzschild radius. And if that happens, then the density of that thing is so big, the gravity is so strong that light can't escape. And you have a black hole.
So they're like tangible objects like that in our world.
Not in Earth. I think you can have anyway, that's completely off topic. Sorry, guys. You can't have like microscopic black holes though. Anyway, what's the probability of being dealt a hand with 3 jacks and 2 kings? 3 jacks and 2 kings. What do you think? What are we thinking?
You just add those over 52.
3. You add them. And is multiply. Yeah. So what's the probability? How many jacks are there?
3.
There's 4 jacks, right? So how many combinations of 3 jacks are there? You have 4 jacks. How many combinations of 3 of them are there? 4 choose 3. So 4 choose 3 times how many kings are there? There's 2, so it'd be 4 choose 2 divided by the total number. Okay. Total number of 3 jack combinations times the total number of 2 king combinations divided by total number of hands possible.
What was the first one?
What is that?
The first 4 choose.
3, right? 3 jacks, right? The total number of 3 jack combinations in a 52 card deck. Since there's 4 jacks, it's 4 choose 3. That makes sense? Times 4. And since it's and 2 kings, you got to do it times the total number of 2 king combinations. And that's always out of the total number of possible hands. Probability of a hand with no face cards. How many non-face cards are there? How many non-face cards are there, Kate Phillips? 40. Yeah, I didn't know the number of face cards. They had to tell me that, so yeah, I also didn't know the number of face cards. It'd be 40 choose 5, right? Divided by 52 choose 5. I went to a casino over Christmas break and last summer.
There you go.
I've tried my hand at it.
How much you lose? If you need any tips, let me know.
I just did slots.
You should play, when we're on spring break, I played blackjack.
Blackjack is like, I can actually like win at that.
Beat the house.
I bet I could be pretty good at blackjack. Probability. Count cards.
Like a 52%.
Is it a sin to count cards? If it's not, I'd do it.
What's the probability?
You're not, you can't, you say you can count.
Is it? I said, is it a sin to count cards?
You could like get in trouble for doing that.
You get in
Yeah,
trouble, but it's
you
a
can't
sin.
get
You get in
arrested.
trouble with God.
You can get kicked out of the casino.
You would get, yeah, you would get kicked out.
How do they prove that you're counting cards though? If you're just doing it in your head,
Just straight
You
with
can
camera.
like, yeah, you can tell.
you can tell.
Hotels.
You can't tell with me. I bet I could do it discreetly.
They like don't let you use your phone.
They don't let you have your phone.
Like if you go on it, you like have to leave the table again.
I can do it without my phone.
If they check the security camera and you're standing at the table watching the game and then you join in and you win most.
Oh,
That's
I could just do cold. I could just join and start doing it.
yeah, just
I don't know.
Oh, yeah, you can like sit and watch
Go to a tux and like go to a casino like a tux and like hair slicked back, high stake, with white gloves on or something. Anyway, what's the probability of this 5-card hand and getting all the aces? Ooh, this is an interesting one. All the aces. Okay. So what's going to happen? Let's think of a 5-card hand with 4 aces. Okay. So we're going to have. We're going to have 4 aces, okay? What's the number of 4, out of the 4 aces, there's 4 aces, what are all the 4 ace combinations? So there's 4 aces, it'd be 4 choose 4, which is 1, okay? And we're going to have 1 extra card from the rest of the deck, right? This is a 5-card hand. So what's the probability, what are all the other, like, 1 cards we could get?
is it 48?
48 choose 1. Okay. Is that confusing? I feel like there's a little leap there. There's a little like logic leap there. Right? So we're choosing out of our 4 aces, we're choosing all 4 of them, and out of the 48 remaining cards, we're choosing 1 of them. That makes sense? When we divide that by the total number of hands possible. Okay, can I do part H? Part H, probability of 5-card hand, 2 10s, 2 jacks, and 1 queen. I think you guys know how to do this one. What do I do for the 10s? What do I do for the 10s?
2 choose 4.
4 choose 2. Right, what do I do for the 2 jacks? How many jacks are there total? And I'm choosing how many of them? So 4 choose 2. And 1 queen, what's that? 4 choose 1. Do I multiply or add all those together? What's that? Why am I multiplying? And. I'm using the word and. Okay, and I divide that by the total number possible. 4. So if they said like, what's the probability of getting like a hand with like all number cards or a hand with all face cards? We can keep those probabilities separately, then add them. Yeah. Or you add and you multiply. All right, what's the probability of dealt a 5-card hand with no aces, no queens, and no 5s. No aces, no queens, and no 5s. So let's think about this. There's how many aces? 4. There's how many queens? How many 5s? So that total is 12, right? So what we want to do, from those 40 leftover cards we have, we want to choose 5 of them, and then we divide that by the total. That makes sense? So how many 5? So from those 40 cards that aren't a 10, or that aren't an ace, queen, or 5, from those 40 cards, how many 5-card combinations can we pick? And then divide that by the total of 5 number. Does that make sense? Probability of being dealt exactly 4 spades. Exactly 4 spades. There's 13 spades to choose from. We're going to choose 4 of them. And then we have 1 card left in our deck that's not going to be a spade. So we're choosing how many cards from that category? We're choosing 1. And then how many non-spades are there? 39. And I multiply them together because a hand with at least 4 spades well, a hand with exactly 4 spades is going to have 4 spades and a non-spade, okay? So then that's divided by 52, choose 5, and then yep. I have to add what to that, though? I have to add what, right? At least 4 spades means we can have 4 spades, or we could have 5 spades. So I'm going to add to that what? What's the probability of getting a hand with 5 spades? Divided by, 52, choose 5. So that'd be my answer. Okay. Are you guys seeing the distinction between or and here, multiplying and adding? Right? For 4 spades, you're gonna choose 4 from the 13 spades, and you're gonna choose 1 from the 39 non-spades. And then you have to add, you could get, since it's at least 4 spades, or you could get exactly 5 spades, so 13 choose 5 divided by the total. You feeling okay? What's the probability of being dealt at most 4 red cards? At most 4 red cards. There's an easier way to do this one that we haven't talked about yet today, but I have talked about it in the past. At most 4 red cards, okay? So we could do this by doing the probability of 1 red card plus the probability of 2 red cards plus the probability of 3 red cards plus the probability of 4 red cards. That's a pain in the butt. What's an easier way to do it?
Can't you just like
I'm going to cancel.
Would it be
I'm going to do 1 minus the probability of getting 5 red cards. Okay. I'm going to do 1 minus the opposite probability. Does that make sense? 1 minus the opposite probability, okay? Right? P1 plus P2 plus 3 P1 plus P2 plus P3 plus P4 plus P5 all have to add up to 1, right? You have to have a 100% chance of getting some number of red cards, right? So I'm going to do 1 minus P5. What's the probability of getting 5 red cards? So how many red cards are there? Aren't there 26 red cards?
Oh, yeah.
So it'd be 1 minus 26, choose 5, divided by 52, choose 5. All right, then M. This one's a little trickier. Anyone have any ideas? Probability of being dealt 2 of one suit and 3 of another, right? So,
Times 3.
so 13 choose 2 times 13 choose 3. Okay, divided by 52 choose 5. You're on the right track. Okay. But there's multiple ways of this happening, right? Right? So it doesn't specify what the suits are. This would be the answer if it was like just 2 clubs and like 3 spades, right? That would be the answer here. But they don't specify which type of suit. Okay? So we're going to multiply this by how many suits do I have to choose from for the first suit? I have 4. So I'm going to do 4. How many choices then do I have for the second suit? 3. So I multiply it by 4 times 3. Right? So for one particular 2-suit combination, this is the probability of it happening, getting 1 of the first suit, 3 of the other suit. But then, right, I have to multiply by the total number of 2-suit combinations that I have, or it's a permutation here. All right, so this 4 times 3, this is 4 permutation 2. Right? Order matters. Getting 2 clubs and 3 spades is not the same thing as getting 2 spades and 3 clubs. So the order that you choose matters. Does that make sense? So it's 4 permutation 2, which is just 4 times 3. Okay. All right. Can I move on to Venn diagrams? Questions, comments, concerns over that stuff? Are we happy? Are we unhappy? I know. For pre-cal class, of course we're happy. Like literally 2 weeks of senior year left. So sad. So. Yeah. Whoa, yeah, let's keep that open. If you want to close it, just probably like that. All right, consider the Venn diagram. Okay. So, yeah, we're going to move into Venn diagrams, okay? They help us think about different like combinatorics problems and probability problems, okay? So let me cover this. Oh, you just test R 11. It says 11:30 for the afternoon test. So let's leave it 10:40. That gives you 50 minutes for each, which is like 15 minutes over the interview.
We have to drive to drive.
Oh, you have to drive?
Yeah.
To Burnett?
Yeah.
See me like I haven't been told anything, so I need to send for it.
Ew, I love Clovis. Clovis is number 1.
It's not number 1. It's not
Yeah.
Number 2. What's above Clovis?
Chick-fil-A. Apparently I get free Chick-fil-A today for like Teacher Appreciation Week.
You should come to my Chick-fil-A.
I do come to it sometimes. All right, we got to move on to Venn diagrams. We're behind. Venn diagrams. Venn diagrams, okay? Got a Venn diagram. Okay, so what's going on here? We got a 30-person class. Okay? Does that make sense? Okay. All right, we split them into the people who like M&Ms and the people who like Twix, okay? So there's 11 people. There are 11 people in our class who like just M&Ms, 6 who like both of them, 9 who like just Twix, 30 total. What I'm going to write here in the corner of the inside of my box is the number who like neither, okay? All 4 of these categories, so I'll highlight them, all 4 of the categories in pink need to add up to 30, right? So what's that number that I should put in the bottom left corner?
4.
Yeah, good job. Wait, right? 11 plus 9, yeah, 4. I don't know how to add, so okay. So there's 4 students who like neither, okay? They just hate the world, okay? So how many like M&Ms? How many like M&Ms? How many students like M&Ms? Just 11? 17. Why is it 17? You got to do 11 plus 6. 17. Yeah. 17. Okay. How many? Yeah. Oh wait. I need to move that down one line. All right. How many like only M&Ms? There you go. Now I do just what? Just copy it down. How many like both M&Ms and Twix? Okay, are we feeling okay about this? How many like M&Ms or Twix? Either M&Ms or Twix. So how many like, when you see the word or in probability, they mean at least one of them. How many like at least one of them? 26. Yeah. Yeah.
What are the fourth class?
People like neither. People who hate humanity, who hate being happy. Okay. I don't want to shame you if you don't like M&Ms or Twix. No judgment zone. But like kind of a judgment zone. No, I'm kidding. I'm kidding. I'm kidding.
Have you seen those like ice creams, like chicken, like the ice cream chicken, like
No.
Ice cream chicken?
like the inside is like a Twix bar,
Can't get that at
ice cream,
Culver's.
and they put like cereal flakes over it, so it looks like a
Send me a link. Send me a link.
No, it's like $100 for like 8.
Yeah.
Don't send me a link.
Don't send me a link. Yeah. Do you have gas? Do you possess gas money? Okay. Do you possess currency for petroleum? Anyway, how many like only M&Ms or only Twix? So how many like only M&Ms or only Twix? So 11 like only M&Ms, 9 like only Twix. So how many fall in either or of those categories? 20. How many like none of them? 4. All right, not a judgment zone, but like kind of a judgment zone. There you go. All right, so let's ratchet up the difficulty. All right, let's ratchet it up. Each of the 28 students in the class either likes jazz, music, country music, or both. Draw a Venn diagram showing the following. How many students like only jazz? 18 students like jazz, 14 like country, okay? Let me think of the best way to explain this one, okay? All right. 18 students like jazz, 14 students like country, okay? There's a problem. There's a problem here if I put an 18 in this circle and a 14 in this circle. What's the problem? It's more than there are students in the class, right? 18 plus 14 equals 32, which is greater than the number of students in the class, okay? So that's a contradiction. Can't have that. The way I do this,
18x plus 14y equals 32.
so I've got to do, there's 28 kids in the class. What I do is I add these two categories up to get 32, and I subtract the total number of students in the class. That gives me how many like both. The number that like both is, so you add the total that like either. And you subtract the number of students minus the number of students. Okay, so 4. That's 4. Okay, and then we can, right, so 18 total students like jazz. So this box and this box have to add up to 18. So what number goes in here? 14. Does that make sense? Okay. This box and this box have to add up to what? 14. So this is what? 10. That's how we do that. Okay. Everyone likes either jazz or country. All right. So yeah. I don't know what else. I don't know what else they want me to do. Yeah, I don't know. Just go on to the next problem, I guess. Sweet. We've been so productive today. Class of 32 students. Surveyed as to the type of car they like. 19 like Fords, 19 like Buicks, 12 like Chevys. 5 like all 3, 6 like only Fords, 3 like only Buicks, 2 like only Chevys. So gosh. All right, so we got to draw a mega Venn diagram here, right? So I'm going to draw a little box. Draw a little box, okay? How many categories are we going to have? How many categories of car are there here? There's 3, right? Fords, Buicks, and Chevys. So I'm going to draw 3 circles. Little. There's like a skateboarding brand whose logo looks like that, right?
It looks like
What?
a toxic,
Oh, toxic symbol? Yeah. So there's 3 categories, okay. All right. All right. 32 students total, right? 32 students total. So 32 total. So we got to fill them in diagram. Okay. So this is Fords, Buicks, and Chevys. Okay. So we know that 5 like all 3. 5 students like all 3, so we can put that in here where there's a 5 in the middle. So 5 right there in the middle, okay? 5 like all 3. Let's see what else we can fill out. 6 like only Ford, so there's a 6 in here. 3 like only Buicks. And 2 like only Chevys. So we have everything except the 3 like wedges here. Okay, so let's just call this X1, X2, and X3. Or let's do X, Y, and Z so it's easier for you guys to distinguish. Call this X, Y, and Z. Okay. We got to fill this out. Okay. 2 minutes left. So 6. I'm looking at the Ford circle here. 6 plus 5 plus X plus Z has to equal what? 6 plus 5 plus X plus Z equals what? 19. Okay. 3 plus X plus Y plus 5. Looking at the Buick circle, what has to add up to what? 3 plus 5 plus X plus Y has to equal. How many like Buicks? No, 19. 19. Okay. Okay. How many like Chevys? 5 plus 2 plus Z plus Y. Do you guys see how I have a system here then that I can solve? How many like Chevys? 12. Yeah, so I can solve that with a matrix and then fill in those numbers. Are you following? Yeah. Wait, one more minute. I'm going to say something. I got to